This review information is about lab skills and kinetics. As you see the little meme, why did the white bear dissolve in water? Because he was polar. So we will talk about making two different kinds of solutions. In the lab we use different pieces of glassware depending on what we're doing. A pipette is a very precise way to measure some small volumes. A burette we use in titrations, and a graduated cylinder is used a lot. It is another piece of precise glassware. If you're asked to pick out of a list of like the most precise measuring instrument of a volume, I would pick a pipette if it's there. If not, I would choose a burette or a graduated cylinder. The burette's probably only going to be there if it's a titration. A volumetric flask is also a piece of precise glassware. It's used to make solutions because it very precisely measures one volume. So as you see, whatever the label is, it has a 1,000 milliliter label. There's an etched mark on the neck, and if you fill to that mark, you get exactly that volume. So it measures one specific volume. Significant figures come from measurements. And there will be a point on the free response section of the AP exam that is purely from significant figures. So if you do not have the correct value of significant number of significant figures, you will not get credit. Occasionally they'll accept a range. Some years it's been a specific number. So my advice is always consider significant figures in your answers, and then wherever that point is, you probably won't know where they're awarding that point. You're going to get that. You'll get it. On the left picture, you see it's a photograph of a burette. The first thing to do is to look at the markings and determine how many markings there are between like 24 and 25. So what value does each mark represent? In this case, they're 0.10. So I noticed the meniscus was below the 0.7 mark, but not quite to the 0.8. So I estimated that second decimal place is to be a 5, so about halfway in between. If you did not include 2 decimal places, you would not get a point for that answer. When you have other measurements, especially like masses, typically you're given a data table of masses. You're probably going to end up subtracting out maybe a piece of filter paper, or in this case it looks like a beaker. Make sure that after you've done that subtraction, based on the significant figure rule for addition and subtraction, that you need to keep the same number of decimal places that you had in the measurements. So again, even if I subtracted and the 4th decimal place was, an understood 0, like it wouldn't show up on my calculator, I would physically need to write in a 0 to maintain 4 decimal places. There are really 2 types of solutions we can make. We'll look at the math associated with the dilution, which is on the left, right here. Notice they're taking, they're pipetting a small amount of a concentrated solution and putting it into a volumetric flask. And then in the second photograph, they're filling to the mark with distilled water. So there's no measuring of the water, you're just filling to the mark, because apparently if you notice this label says 500 milliliters, that this person must have been asked to make 500 milliliters of a solution. And we'll look at the math in just a moment. The second solution is where you take a measured amount of a solid salt and you're going to put it in the volumetric flask. Again, if you're whatever amount you need to make of the solution, that's the flask you would choose. Again, put the solid in, no measuring of the water, you're just filling to the mark, and of course you would need to be swirling the whole time you're adding the water, just so that you'd make sure that the solid dissolved. Here's the dilution formula. So again, you're going to know a beginning molarity and volume typically, and maybe you're asked how, what's the ending volume going to be, or what's the new molarity. You'll know 3 of the 4 numbers and be solving for the 4th. Again, make the solution in a volumetric flask, choose the flask of the amount of the solution you want to make, and you can see as that picture is highlighted, make sure the meniscus touches the mark that's etched on the neck of the flask. I gave an example there. If you're asked to pipette 1 milliliter of a 1 molar solution to make a total of 10 milliliters, okay, and it does say by adding 9 milliliters of water, that 9 milliliters of water would not be measured. Again, we would choose a flask of the new volume we wanted to make, so we want to make a 10 milliliters total, so I would pick a 10 milliliter volumetric flask. I would pipette 1 milliliter of the concentrated 1 molar solution into it, and then add enough distilled water that would fill to the mark and make the new solution. So the question is, what is the new molarity of the diluted solution? So it's a way to use that dilution formula. So there's the math associated with that. So again, the first volume is the small amount of the concentrated, and then the second volume is the total volume that I'm making, which would include the concentrated plus the water that had been added. You might be asked to take that solution and to dilute it even further. So if you're asked to repeat the same procedure, but this time you would take this 0.1 molar solution, pipette out 1 milliliter of it into an additional 10 milliliter volumetric flask. Notice the only thing that would change for this next math problem would be the molarity here. So it would literally be the same math with this 0.1 molar replacing the 1 molar solution. So when you did the math, notice it's a tenth of the molarity of the previous one. If you're continuing to do this, that's called a serial dilution. If you take the same amount and keep diluting it and over, and again, this is a way we use this to make a standard curve, which you might have seen that, or maybe you did a lab involving absorbance of light of colored solutions. Basically, we would have, as you see on this, they had 4 standard solutions where, some, as you notice, you can see that standard 4, its concentration and absorbance are the lowest. So that would have been the most dilute solution versus standard solution 1, which has the highest concentration and therefore the highest absorbance. So again, if we use that procedure on the previous slide, we could make these standard solutions. This is where you had a cuvette that you rinsed and put in the colorimeter to monitor how much light the solution absorbed. The greater the concentration or the darker the color, and again you have to have colored solutions, the more light that was absorbed. And once we know we have this standard curve, then we could put an unknown in a cuvette, put it in the colorimeter, and see, as you see this dark line, we could just see where an unknown would fall on the line, and then we would also know, based on the unknown's absorbance, what is its concentration. And that's called Beer's law. And again, here's your formula. It's a direct relationship between absorbance of light and little c is concentration. A and B are constant, so it's, they're defined here, molar absorptivity constant. The path length is just the distance, 1 centimeter the light's traveling. A and B aren't going to change. It's just that the absorbance and concentration are directly related. Here's an example question. Using the absorbance versus concentration graph given above, a student is trying to determine the concentration of an unknown substance. If the student measures the absorbance to be 0.4, what would be the concentration of the unknown? So again, it's just literally reading a graph. Even if you've never done this lab, it doesn't really matter. We'd find where 0.4 is. We'd go to the line, come down, oops, I'm a little over, and estimate the answer. It looks like it would be about B, 0.28. Now we're going to jump into kinetics. The collision theory, and sometimes when you're learning reactions in the beginning of honors chemistry or pre-AP chemistry, you don't really think about reactions cannot occur unless molecules collide. What's happening is the bonds have to break, new bonds have to form, but it's not just any old collision. Some collisions, just the molecules actually just bounce off one another and nothing happens. the collisions have to have two very important components. First, there has to be enough energy there to break the bonds in the reactants, and we call that activation energy. And you can see the top of the hill is the minimum amount of energy that have to be present. And then the other important characteristic of a collision is that the molecules actually have to collide at a correct angle, or we call that orientation, so that the bond breaks. And so here's, if you look at this energy diagram, this is the reactants right here. If there's enough energy in the collision, which is noted by the distance here, that's the distance from the beginning to the top of the hill, that's our activation energy. The correct bonds can break, the molecules can reform, and notice that in this case the products end up with lower energy. So this is actually showing us an exothermic graph because the products ended up with less energy than reactants had. So the difference between those two, if you notice, it says delta E, we'll call that delta H, that's the enthalpy change in the reaction, and that's going to be negative. Kinetics is all about how fast reactions occur, which we call rate, and we can speed up reactions. If we increase the temperature, there's more energy present, more of those collisions would have enough energy to form products. Number two, if we just had more concentrated reactants, if there's more concentration or larger amounts of reactants, there's going to be more collisions and more opportunities for those collisions to be successful, meaning form products. The reactants themselves have to have good ways to come in contact with one another. If I have a solid reactant and it's in big chunks, it can't really adequately come in contact with other reactants. So that's why we're saying the surface area does matter. So a powder would react faster than a solid that was in larger pieces. And number four, adding a catalyst. This really isn't part of the reaction, but the catalyst provides a new pathway for the reaction that has a lower activation energy and therefore causes the reaction to speed up. One thing that could be mentioned, and a lot of times in multiple choice, is an inert gas, and an inert gas would be like a noble gas, argon, or any of those that it might be added to the reaction container. Again, don't let that fool you. It's just a distractor, and it does not have any effect on rate. Also, as we'll talk about later, if we have a reactant that has a zero order reactants also do not have any effect on rate, so it doesn't matter if we double their concentration, the rate would stay what it is. Okay, here's an energy diagram that includes a catalyst. Notice this catalyst, even though it has these two hills, both are lower than the uncatalyzed reaction activation energy, and the question is, what does the double hill represent? So as you can see, two intermediate products are probably being formed here before the actual products are being formed, and so that's really representing a two-step mechanism. We'll look at the end of the document. And the other thing I wanted to note here is that other things aren't changing because the rate changes. So notice where the reactant started and the products end, that delta H value is going to stay the same. Free energy is not affected, and capital K, which is the equilibrium constant, is not affected as well. And there we go. You see that it says the reaction has two steps, and as you see, the higher the hill, the slower the step. So this is a two-step mechanism, and we could see that the second step must be slower because it has a higher activation energy. Any kind of rate is something happening in a time period, and so for our purposes, rate of reactions typically are the change in concentration, and we represent concentration at molarity as brackets, divided by the change in time. It could be a change in pressure over time. It could be a change in absorbance over time. Again, it's a change in something we can measure in a time period. That concentration or molarity is the most common. Rates are represented as positive. They're called the rates of appearance for products because products are, being formed, they're showing up. And a negative sign is used for the rate of disappearance of a reactant, because if you think about anything that's delta, it's final minus initial. We don't want a negative rate value, but we would add a negative sign in front of this term for reactants so that when we subtracted a final minus initial concentration, we would have a negative value multiplied times this extra negative sign would give us a positive rate. Here's an example question. Given this ozone decomposition reaction of ozone going to oxygen gas, if the rate at which oxygen appears, and it's showing you the change in, notice that's a positive statement. It has no, because that's a product appearing, so it's a positive change, is, and it gives us a value at a particular instant. At what rate is ozone disappearing at the same time? So again, we're going to relate these to each other based on their mole ratios. And notice ozone is 2/3 the rate of oxygen, and the way I got that was I actually just set up a mole ratio. So I started with the rate of oxygen appearing, which is given in the problem. Since I started with oxygen, my mole ratio would have oxygen on the bottom. I'm solving for ozone, so it's 6.0 times 10 to the negative fifth times 2 divided by 3, and that's how I got the answer. We will be given data, rate data, and concentration data of reactants. Notice Kinetics is all about reactants. We only mention how products form. We always start measuring the rate of a reaction at the beginning of the reaction. That's where it's going the fastest. That's where we had the most reactants present. And you're going to be asked to write a rate law, and to do that we need to figure out the orders, or what effect each reactant will have on the rate of the reaction. So these are just some definitions really. A reactant is zero order, which means, and that's going to be an exponent. If we double the concentration, it has no effect. A first order reactant is like a 1 exponent. So if we double the concentration, it actually would have the effect of doubling the rate of the reaction. And if a reactant is second order, that would be like an exponent of a 2. So as you see, it's the change in the concentration causes a square to the rate change. So if the concentration doubles, the rate quadruples. Here's an example of what a data table might look like. Notice there are 2 columns of concentration data, there are 2 reactants, and then here's our rate information. So there's lots of trial numbers, okay, and one thing to notice is that you'll see in several trials they'll keep one reactant constant and they'll be varying the other. And you really can think about this as a control group. If I keep one of the parts of the experiment the same and I vary the other one, I can tell if, like in this case, it is the ammonium ion affecting the rate of the reaction. And I would know it's ammonium affecting the rate since the nitrite ion was held constant. So if you see the first statement, if we compare experiments 1 and 2, we see that the ammonium ion concentration is doubling. Okay, don't need a calculator. You can just see it's, hopefully you can just see that it doubles. The nitrate ion is held constant, and what's happening to the rate? It's doubling, so that must have been because of the ammonium ion. There's nothing else that was changed. So that is what it looks like as first order. When we compare experiments 5 and 6, now this time we want to look at experiments where, notice, these are held constant, and we want to notice that the nitrite ion is changing, and how is that going to affect the rate. And again, I picked 5 and 6. You might want to pick 4 and 5. Again, I try to look for data that has an easy change to recognize. Like if you looked at 4 experiment numbers 4 and 5, or 5 and 6, you would see that both involve doubling, and also the rate is doubling. So therefore, nitrite ion is also first order. If you were asked on a free response question to explain how you're determining the rate, you have to write a rate law, but to do that you have to determine the orders of each reactant. These statements are your explanation, your evidence. You're just explaining the patterns you see in the data, and that would get you credit for your coming up with both of the reactants as being first order. Now, once we know the orders of the reactants, we can write a rate law. A rate law is a formula that describes how everything's affecting that reaction. So make sure you have to have the word rate equals. You have a lowercase k, this is the rate constant, and then I have my two reactants in brackets with their understood, in this case, orders of 1. You know, if you don't have to write that since it's a 1 exponent, but if it was squared, obviously that would make a difference and I would have to include it. So K is the rate constant. It only changes with temperatures. If you're asked to write a rate law, you might be asked to calculate the value of K. If we go back to, see, we have this rate law now. If I was asked to calculate the value of the rate constant, I would go back to the data and I'd probably just pick the first line of information from trial 1. So I'd take the rate law, I'd plug in the ammonium ion concentration, the nitrate ion concentration, and I would replace the rate with its value. And then I would have all of this filled in, solve for K, and keep up with your units because the units would probably be a point as well. All right, so when we're talking about reaction orders, we can really only determine those from experimental data, so like we were doing. Another way to determine a reactant's order is to make 3 graphs of the data we have. Okay, so like if I take the concentration of one of my reactants and I plot its, concentration, how it changes with time, and then I take the concentration and I calculate the natural log of the concentration and plot that versus the time, and then the reciprocal of concentration, or 1 divided by concentration versus time. If I make these 3 graphs, the graph that gives me the best line, because some of them might look like a curve, but I'm looking for a graph that gives a line. And as you can see, this first graph is a line, and the other 2 have some curves to them. So just by seeing that this is a line, and this has been a free response question before, it's like, what is this reactant's order? Well, I just look for the graph that has the line, like this question asks. What is the order of this reactant? Well, I just have to know which order is represented by each graph. So just the regular concentration versus time graph is a 0 order graph. Natural log of concentration versus time is a 1st order graph, and then 1 over concentration versus time is the 2nd order graph. So since the first is a line, I would answer the reactant must be 0 order. Since that graph, concentration versus time, gave a line. If I double that concentration, since it's 0 order, so literally that's a 0 exponent, anything raised to the 0 power goes to 1. So that reactant would have no effect on the rate of the reaction. So I could double the reactant's concentration, I could quadruple it, the rate would not change. On the formula sheet, there are these 2 formulas, and as I've explained in these words below, you can see that the natural log of concentration and 1 over concentration, those refer to these 2 graphs if they were aligned. So here's our line slope format. I've just tried to show you, unfortunately, that's how we learn it in math. All they've done here to change this is they just subtracted the y-intercept to the other side. So this is really a y minus b equals mx. So if we know the slope of, if one of these graphs was a line, so again, this is our 1st order graph, and this is 2nd, and conveniently they're in the right order. 1st is the 1st order graph, 2nd is the 2nd order. If we know, one of these, we can figure out the slope of the line, and we would know the rate constant, because notice the slope is, if we go back to the other slide, K does give us the slope. So this is a line. Notice that was a 0 order graph. We don't actually have that formula. But these first 2 graphs, the 0 order graph and the 1st order graph, both have negative slopes. So if I knew the value of the negative slope, I would multiply times -1 to get the rate constant. The only graph that gives a positive slope if it was aligned is the second order graph. There is this half-life formula that only goes with a first order reactant, and really what half-life means is the time it takes for half a reactant to react, and then that means half of it's left. Okay, so the one thing that's unique about first order reactants, and this also does this with nuclear decay and with pharmaceuticals, most drugs are first order reactants, is that when half of the time it takes for half of the reactant to react is consistent. So like if I started with 100 grams of something and it went through a time period at its half-life, at the end of that I'd have 50 grams left. It went through that same time period again, I'd have 25 grams left, then 12.5, and so on. Only for first order reactants. You might be asked to find a rate law from a mechanism, or maybe just be asked questions like which mechanism is the best choice for this rate law. Kind of some different variations to how this can be asked, but you just need to know how to interpret a mechanism. So a mechanism is two or more individual reactions that we can add together, as you see in number 1, that have to add together to get an overall reaction. Kind of sounds like Hess's law, okay? The other thing that has to be correct about the mechanism is that the mechanism must agree with the experimentally determined rate law. So in other words, in these mechanisms, a lot of times you'll be told there's a slow step. Okay, the slow step is determining the rate. The whole reaction cannot go any faster than that slow step. So if the slow step is first, and we'll see this on the next slide, that is the rate determining step. So the reactants in the slow step would actually match the orders in the rate law. However, as you see from this last statement, the rate law is determined by all steps through this slow step. So if you had a 3-step mechanism and the slow step is second, what occurs is that the slow step is slowing down the first step. It's like a bottleneck. So you'd actually have to consider any steps before the slow step and consider those as part of the slow step. Simply, if the slow step is first, I look at the reactants in the slow step, and since I know slow step is determining the rate, first, I'm getting ahead of myself. Based on the mechanism, what is the overall reaction? Basically, all I'm going to do is add these together. When I add these together, I can see that this cancels and that cancels, and one of these is going to cancel. So what's left is NO2 plus CO yields NO plus CO2. So that would be my overall reaction. The rate law is determined from the slow step. Okay, so in this case, the slow step, we can see that there are 2 molecules in the slow step. So this rate law would be rate equals K, and then I would say NO2, and it would be second order since there are 2 molecules. Okay, it says, is there an intermediate in the mechanism? The intermediate is any substance that, like the NO3, that was first made and then was completely used up. So it's not in the overall reaction, and so it's kind of an intermediate or temporary product. So it's made and then immediately used. A catalyst would be like one of these molecules of NO2. One of the molecules is, notice it's present at the beginning and present at the end. So it's really not in the overall reaction because it was just present to speed up the reaction. But since this was in the slow step, which was rate determining, that meant that it was part of the rate law, and that's how NO2 was second order. And here's the explanations on the next slide.